This is a talk about space. And everybody knows that space is big, and it's black, and it's empty. But actually, that's not entirely true, because although space certainly is extremely large, not all of it is black. So this is an image from the Hubble Space Telescope. And what you can see here is gas and dust and plasma surrounding an exploding star. Here's another, again, another nebula around a star. And here's another again. This is actually part of the Orion Nebula. This is about 1,300 light years away from us. And this is the nearest star formation region to us. So stars are actually being born in this nebula as we speak. And what you can see here is a very complicated dynamic environment. And in fact, it's turbulent. And we'll come back to that later on. So as you can see, it's very structured. And there are lots of structures on lots of different scales. You can see kind of dark bits of dust and gas. And also there is plasma here as well. And in fact, although this is a particularly dense part of our galaxy, and not all of the galaxy looks like this, nevertheless, everywhere we look in space, we do see some material. So between the galaxies, between the stars in our own galaxy, and even between the planets in our own solar system, everywhere we look, there is material. And that material is almost always in the plasma state. So that's charged particles, protons and electrons. And that's what I'm going to be talking about today, the plasma in space. So where does this plasma come from? Well, in our own solar system, it actually comes from the sun. So the sun itself has a hot upper atmosphere, and that atmosphere expands off into space and forms a continual flow called the solar wind. And that actually blows a bubble in interstellar space. And as the sun and all the planets travel at about 30 kilometers a second through interstellar space, that bubble drives a bow wave, a compression wave in front of it as we travel through the galaxy. And in fact, the sun isn't the only star that does this. Lots of stars do this. And actually one in this picture. So if you look at that star there, if I zoom it up, in fact, you can see the bow wave in front of it. So this star is traveling right to left. So a very similar interaction is happening in our own solar system. So you are down near the middle of that. OK, so the sun produces the solar wind. But how does it do it? How does this happen? Well, most of us, when we think about the sun, we think of something a bit like this, if we're lucky enough even to see the sun. So the sun is a fairly featureless yellow ball in the sky. So it provides all the light and heat and energy that drives almost all of the life on Earth. But nevertheless, it's a pretty boring object. It's been known for thousands of years that occasionally there are very large dark spots on the sun. But it wasn't until the advent of the discovery of telescopes in the 1600s. And so, for example, Galileo started looking at the sun on a regular basis and realized that these sunspots actually move across the disk. And this is because the sun rotates, so it rotates about once a month. So what you're looking at here is the hot, visible surface of the sun. It's at a few thousand degrees, and this is what's known as the photosphere. But as you can see, there's really not a lot happening here. It's relatively boring. But this isn't everything that's going on in the sun. This is by no means anything like what's really interesting on the sun. Because the sun has this hot upper atmosphere, and that atmosphere is so much more dynamic than the photosphere. That atmosphere is called the corona. So this is a movie of the corona. And this is a movie actually taken in ultraviolet light. Now, we can't see ultraviolet light down here on the Earth, not only because our eyes aren't sensitive to it, but also because the atmosphere actually blocks ultraviolet light. So there's no way you could take an image like this from the surface of the Earth. So we have to go into space to take a movie like this. And this is a movie taken by NASA's Solar Dynamics Observatory spacecraft. And this is speeded up to make the sun rotate in a reasonable kind of time scale. But you can see, I hope, on this image, a great deal of structure. This is so much more dynamic than what we saw earlier in the photosphere. So there's structure on many scales here. We can see kind of dark regions, light regions. They're all varying around. The bright regions are there because there's more plasma there. And actually what you're seeing here is you're seeing emission from extremely hot plasma. This is at hundreds of thousands of degrees. And one of the characteristics I hope you can see here is that there are lots of loops. So if you look at this, what's called an active region here, you can see lots of loops connecting things. Those loops, we're seeing enhanced emission from those loops because there's additional plasma on them. They're just a bit denser than their surroundings. And the reason they look like little loops is because the plasma is actually tied to a magnetic field line. What you're actually seeing here, essentially, are magnetic field lines coming out of the sun. So this very complicated, tangled picture that you see is really the result of complicated, tangled magnetic fields. So these loops and the way that the magnetic field constrains the plasma are going to be a recurring theme of this talk. So clearly, then, this is a very structured and dynamic medium. There's a lot going on here. But we can't see this from the Earth, as we've said. apart from at very occasional times. And those times are during total solar eclipses. So here's a picture of a total solar eclipse. So this is when the sun entirely blocks out the visible light from the, the moon blocks out the visible light from the sun. And if you've ever seen an eclipse, you know that around the moon you see this kind of halo of this blue glow, and that's what you can see here. And this is what was originally called the corona. So corona means crown in Greek. And this corona, what we're actually seeing here is visible light, sunlight, scattered off electrons in the upper atmosphere. So clearly we can see then this corona extends much further than what we could see in the previous movie. In fact, it extends out to large distances. And in fact, this corona is so hot, and its pressure, relatively speaking, is so high, that it actually expands and accelerates off into interplanetary space, and that's what forms the solar wind. So it's the sun's hot upper atmosphere expanding and filling the entire solar system, and in fact that goes out far beyond all the planets, including Pluto, so it fills a large volume of space with this plasma that originally comes from the sun, from the corona. So it accelerates as it goes, and it gets pretty quick. This is a movie, again, by another spacecraft. This is actually by a spacecraft called Stereo, using an instrument called the heliospheric imager, which was largely built in the UK, actually. And the sun is off to the right-hand side in this image. And what we're actually seeing, again, is scattered light from the photosphere by the density variations in the solar wind, but much further away from the sun now. And what I hope you can see here, although this is incredibly faint stuff, you can never see this from the surface of the Earth. You have to get into space to see it. And these are very delicate, deep cameras to be able to take these measurements. Nevertheless, you can see a great deal of structure here. So there are all these little blobs going past all the time. So the solar wind is by no means a smooth flow. It's very structured, and it's very dynamic again, just as we're seeing from plasmas generally. Another thing you might be able to see starting over here on the left-hand side, this is a little comet. This is Comet Encke. And Comet Encke dives around to about a fifth of the distance of the Earth from the sun as it comes around this trajectory. And as you can see, hopefully, the tail kind of waggling around as it does so. So that's being waggled around by the solar wind flow. So you can see the solar wind is roughly radial, but it's a bit variable. Again, it's quite structured. The other thing you can see, there's actually a transient event comes off the sun called the coronal mass ejection. It's going to come off in a minute, and Encke's tail actually falls off when that happens, if you wait for it. There you go. Falls off, and then it grows back again afterwards. So this solar wind flow is then traveling outwards at very high speeds from the sun and past the Earth and into deep space. And it's traveling very quickly. So it's traveling at something like 300 or 400 kilometers per second on average. Some of it's a bit slower, some of it's quite a lot faster. So that's pretty quick. So it's hard to kind of get your head around what 300 or 400 kilometers actually kind of means. But for example, if you lived in Oxford and you wanted to go to Zanzibar, for example, that would only take you about 20 seconds if you traveled that quick. If you lived in Croydon and you wanted to go and see your aunt in Australia, that would take you a bit less than a minute. So this is actually very quick stuff. So, and in fact, this evening, when we want to go home at the end of what will probably be quite a late night, I could get home in less than a tenth of a second. So that's going to feel, if only we could do that by the end of the evening. Okay, so it's very fast. But as well as being fast, it's actually very rarefied. There's very little stuff here by the time it gets out towards the Earth. So if you take a glass of water like this, this has got lots of molecules in it. It's got lots of protons and electrons in it. The solar wind has very little. So in fact, in the solar wind, the density is just a few particles per cubic centimeter. So if I took all the particles in this glass of water and stretched them out so they were at the same number density as the solar wind by the time it arrives at the Earth, then they would be on the way towards the size of the moon. So there's really very, very little material out there in interplanetary space. There's almost nothing. And in fact, its pressure, therefore, is extremely low. So it's something like a billionth of the atmospheric pressure in this room here. It's incredibly low. And in fact, the pressure from the sunlight reaching us from the sun is actually considerably larger than it is from the solar wind. So really, the solar wind is completely negligible from that point of view. So then, is the solar wind unimportant? Does this not matter to us? Well, actually, that's not true. The solar wind turns out to be extremely important. So along with the particles that are coming from the sun, they carry with them the magnetic field from the sun. And sometimes that magnetic field can be at an orientation such that it connects into the Earth's magnetic field. And that lets solar wind plasma get close to the Earth, and those particles actually can get accelerated, drop down field lines to the top of the Earth's atmosphere and hit the molecules there. And that causes them to glow. And that's what causes the aurora. So this is a movie from the International Space Station flying over the aurora, and you can see It's becoming a bit of a recurring theme that plasmas are complicated and dynamic and tangled. You can see really just how variable these things are. So the particles are streaming down magnetic field lines and hitting the top of the atmosphere. So this is all quite nice, this is a pleasant thing to see. But not everything that the sun does via the solar wind is quite as pleasant as that. So the sun can actually have some negative effects on us because we are increasingly dependent on technology. And a lot of that technology is now in space. So some of the negative effects from the solar wind and its magnetic field, for example, can damage spacecraft. They can knock out spacecraft in orbit, so they can interrupt satellite communications, satellite television. They can also disrupt satellite navigation systems, the TomTom in your car. They can also actually have effects on the ground as well, so it's not just in space. So actually they can have effects on power grids and disrupt them. They can also, for example, disrupt the drilling of oil wells. So there's a wide range of technological effects that come from the variability on the sun and the way the solar wind interacts with near-Earth space and with our planet itself. And these effects are collectively known as space weather. And space weather is something that's growing up the national agenda and, in fact, worldwide. And it's something that, as we become more dependent on technology, is something that will become more and more important to us. So I'm not going to talk any more about that today, but that's one of the reasons why the study of space is of interest. What I really am going to talk about today is plasmas in space and one particular phenomenon in plasmas. So plasmas, it turns out, as we'll see, we can treat essentially as fluids, and they do many of the things that other fluids do. They can support shock waves and regular waves and so on. And one of the things that they are is turbulent. So what I'm going to be talking about today is plasma turbulence, so turbulence in plasmas in space. So if we're going to understand plasma turbulence, we need to understand a bit about plasmas and a bit about turbulence. So let's start with plasmas. Most of us aren't very good on plasmas, and that's because we don't really come across them day to day. So if you take something solid like this desk, or a liquid like a glass of water, or indeed something like the air, a gas like the air, all of those things are made of molecules and atoms. And the atoms themselves are made of nuclei, or nucleons, which are neutrons and positively charged protons. And surrounding them are electrons, which are negatively charged. So in the simplest case, hydrogen, we have a proton in the center, which is positively charged, and a negatively charged electron. And the electron is bound to the proton because those two opposite charges attract each other. Now, charged particles are sensitive to electric and magnetic fields. And so you might think, therefore, that atoms are sensitive to electric and magnetic fields, but actually they kind of aren't so much. And that's because there are always equal numbers of positively charged protons and negatively charged electrons in every atom. So, for example, if I put an electric field across this hydrogen atom, then the proton will feel, because it's got a positive charge, it'll feel a force along the electric field direction, but the electron, having a negative charge, will feel a force exactly equal in the exact opposite direction. And so the net total force is zero, so this atom actually fundamentally isn't very sensitive to electric fields. And it's kind of the same with magnetic fields. So if you're going to get a medium which is actually sensitive to these electric and magnetic fields, you have to basically rip the electrons off atoms to make them charge. So we have to find a way of getting this electron off this proton. And actually that's really hard to do. These are very tightly bound together. So the simplest way to do that is to make them very hot, and eventually they'll jiggle around enough and the electrons will fall off. But that's actually quite tricky. The temperature need to do that is a few thousand degrees, and we just don't come across temperatures like that on the Earth most of the time. The other thing we could do is actually put a sufficiently strong electric field on here that we tore the electron. And that doesn't really happen in nature very often. The one time that we do know when that happens is during a lightning strike. So a lightning is basically caused by a sufficiently strong electric field that it starts tearing electrons off atoms. And in that case, it drives very strong currents. It actually heats the air incredibly hot, generates a plasma. And the expansion of that generates the shock wave that we hear as lightning. But we know that lightning flashes are incredibly short, and that's because the protons and the electrons very rapidly recombine to form neutral atoms, because there's so much stuff around, and in general, it's not very hot. So we really can't sustain plasmas on the Earth in day-to-day life like this. It's incredibly hard. So that's why we don't see them on the Earth. We're not used to things that are susceptible to electric and magnetic fields. But it's different in space, and in fact, the solar wind is at hundreds of thousands of degrees. So in that case, it's effectively fully ionized. So we're really looking mostly at protons and electrons, and those charged particles are susceptible to electric and magnetic fields. And in particular, the magnetic field is very important. So if I've got a charged particle like a proton, and it's moving in a magnetic field, then it feels a force, and that force is perpendicular to its motion, but also to the local magnetic field direction. And what that means in practice is the particles gyrate in little spirals around the magnetic field. So here's a proton gyrating around the field. It can also travel along the magnetic field. And in plasmas, there's loads of particles. So they're all sitting there gyrating around the magnetic field all the time. So we've got billions and billions, uncountable numbers of particles all gyrating around. But as you can see, they're all tied to the magnetic field line. So just as we saw in those movies of the Coronal, where we could see the magnetic loops, because the plasma was tied to those loops. So it's the same here. The particles are essentially bound to the magnetic field lines, and they follow where the magnetic field lines go. And that's very important for their behavior, as we'll see later. OK, so there's lots of particles here, and they're all gyrating around, and they're all doing their own thing. How can we possibly understand this medium? How can we make any progress in trying to understand what happens here? Well, in fact, there are various approximations we can make on various scales. And one of them that's particularly convenient is if we look back on this plasma and we stand back far enough to look at scales considerably above what's called the gyro radius, the scale at which these particles gyrate around the magnetic field line. So if you look at sufficiently large scales, we don't have to worry about that gyro motion. And it turns out, under certain conditions, which actually are very well satisfied in the solar wind, we can essentially treat this medium, therefore, as a fluid. So we can talk about its bulk properties, like it having a velocity and a density and a temperature. And that makes things an awful lot easier. So the kind of scales I'm going to be talking about today, we can really treat things as a fluid. So that fluid is still susceptible to electric and magnetic fields. So it doesn't behave exactly like a neutral fluid. It has particular quirky properties because it's made of ionized particles, but at least it makes a tractable thing to study. And that's known as a magnetofluid. And the topic of study there is called magnetohydrodynamics. OK, so that's the kind of plasma that we're going to deal with. We're going to deal with it as a fluid. Now, one thing you might think is, well, OK, so we can treat this as a... Why do fluids behave as fluids? Why do fluids exhibit the bulk collective motion that means we can talk about them having velocities and temperatures and so on? They do that because the particles collide with each other. They interact with each other and they exchange momentum and energy. And that means that it's possible for them to exhibit this collective behavior, for example, to have thermal distributions of velocity. The solar wind is so rarefied, just a few particles per cubic centimeter, that actually the particles effectively never collide with each other. So the mean free path of these particles is roughly the distance from the Earth to the Sun, on average. So these particles essentially never collide. So how then can you have collective behavior in a medium where the particles don't interact with each other? If that was if they were neutral particles, if they were atoms or molecules, you couldn't have collective behavior. But in fact, you can in a plasma, and that's because the particles interact with each other because they're charged. So the motion of charged particles generates electric and magnetic fields, and those magnetic fields then influence the motion of other particles within that medium, which then change their motion and generate electromagnetic fields, which go back and so on. So the particles actually communicate at a distance with each other via electric and magnetic fields. Again, that's very different to a neutral medium, but it means that actually they can exhibit bulk behavior, even though they never collide with each other. OK, they do other things too, and one of the important things that plasmas do is they support waves and different types of waves compared to those that we see in a neutral fluid. And again, that's because of the presence of a magnetic field. So there's a range of different wave modes. The most important one, and the one we're really going to be thinking about today, is something called an Alfvén wave, which was first predicted by Hans Alfvén. And that's a wave which propagates along magnetic field lines as a result of the magnetic field line tension. So we're going to try and demonstrate this for you, not with a magnetic field, but with two of my helpers here. So if Aisha and Hannah could come down, please. Thank you very much. There you go. So what we're going to do is here we're going to use a slinky coil essentially as a magnetic field line. Okay, so magnetic field lines, like a coil like this, or also like a guitar string or a violin string, they have tension. They want to be straight. And so it means if I twang it, it'll vibrate. And it'll oscillate, so just like a guitar string. But as well as just oscillating like this with a standing wave, in fact, they can actually support waves that propagate along them as well. So if Aisha gives her end a bit of a wiggle, give it a really good wiggle, you can actually make waves travel along the magnetic field in this way. Okay, and if Aisha stops and then Hannah does the same thing, waves can travel nicely done. Waves can travel in both directions along here, okay? And the restoring force of this wave is the tension in the magnetic field that makes them propagate. Now, those waves are actually stable. So if I've got waves traveling one way along the magnetic field, they'll just kind of keep going. The same on the other way. But if we have waves going in both directions at once, there you go, it all goes a bit mad, and those waves actually nonlinearly interact with each other and they decay, and that's going to be important for the turbulence later on. Okay, excellent. Thank you very much for the demonstration. Thank you. So then we've seen, so there are waves in the plasma, and as I say, that'll be important for us later on. Okay, excellent. So that's everything we need to know about plasmas. So let's talk about turbulence. So turbulence is actually surprisingly difficult to define, although it's one of those things that you know it when you see it. So my dictionary defines turbulence like this: a state or condition of confusion, movement, or agitation. That's actually a worryingly good description of my life, but if we ignore that, this kind of isn't what we mean, but it's a very negative term, right? So these, all the synonyms, they're all negative things, and the antonyms are all positive things. So this isn't, we don't have a good view about turbulence from this point of view. But this isn't the kind of turbulence that I'm really talking about today. So what's the kind of turbulence we're talking about? I'm talking about turbulence in fluids. And turbulence even in fluids is something that a lot of people sort of don't have a very good idea about. So if you hop onto Google and have a quick look and see what people think of when they think of turbulence, it turns out they mostly think of this. So turbulence is the thing that makes the captain put the seatbelt sign on, which means we don't get our gin and tonic, right? So that's what most of us think of as turbulence. And that turbulence is the turbulence that we feel on a plane is due to large-scale motions in the atmosphere of the Earth. So the air is moving around because of convection or velocity shear, whatever it might be, and that generates bumps that we feel as we fly along on the plane. But actually, the planes themselves generate turbulence as well. So not by design, you know, ideally we'd have planes that produce a completely smooth flow over them, because the turbulence itself, the disordered motion of the fluid that the planes generates drag. It produces drag and it slows the planes down and it makes them less efficient. So airplane designers don't want drag, they don't want to produce turbulence, so they try and make the flow of a plane as smooth as they possibly can to make them as efficient as possible. And actually some of the most efficient planes in the sky are gliders. So this is, you can see just how sleek these shapes are. They're designed to make the airflow as smooth as they possibly can be, to reduce the turbulence as much as possible. And these are actually remarkably efficient machines. This one, incidentally, is owned by Imperial College, amongst others. So it's a very smooth flow, and that makes them very, very efficient. So glider pilots wanting to travel a long way actually get slightly obsessed by making these things as efficient as they can, so they clean them to reduce the friction. And they even get annoyed when insects, sacrifice themselves on the leading edge of the wing, and that actually noticeably reduces the efficiency of the wing. So these are really very efficient things. And sometimes gliders, just like regular airliners, are actually too efficient. And sometimes we want to come down, and if you want to come down in an airliner, then sometimes they put out the spoilers and the flaps come down or whatever else to add to the turbulence, to make more drag, to help get them down on the ground more quickly. So turbulence in that sense is a useful thing as well as a bad thing. And of course, there's nothing new under the sun, so nature's known about this for a long time. So this is a puffin on short final, so full flap, spoilers out, gear down, ready to land. So this is a case where turbulence is a good thing. Okay, turbulence isn't always a bad thing. But we're still not really getting a lot further towards understanding what turbulence really is. Let me give a bit of a demonstration. Let me go onto the visualizer. So we all sort of know what turbulence is because we've all sat in the bath when we were kids and splashed around, and that makes turbulence. If you've got a kitchen that's as old as my kitchen, then you make turbulence every night when you do the washing up. So you put the washing up liquid in the bowl and you kind of slosh it around. And by sloshing it around to mix the washing up liquid into the water, what you're also doing as well is you're putting energy into it. So you're producing a large-scale motion. And we know that if you do that, you generate the large-scale motion, and then you just wait. Eventually, it'll all go away, and it'll settle down again. So what's actually happened? Well, those large-scale energies have gradually been dissipated away by essentially friction within the fluid, which is what we call viscosity. And that viscosity eventually damps out those motions. And ultimately, that energy has gone into heat in the water, but it's a very small amount. So viscosity is the enemy of turbulence. So in fact, if you think about the sloshing motion, they have a certain amount of energy, and there's a kind of inertial force associated with a certain level of motion. Then there's a certain force as well associated with the viscosity trying to slow them down. And the ratio of those two is what's known as the Reynolds number. So if that force is sufficient, if that ratio is sufficiently high, the motion, the inertia of the system actually is much stronger than the viscosity, and so the system will stay turbulent. So let's see that in action, and in fact we can see that the importance of viscosity in damping out turbulence, and we can see that with tomato soup. So let's give it a go. So there's a bowl, there's some soup. It worked earlier. I don't know if it's going to work now. So soup is quite viscous, right? This is Heinz tomato. OK, so what I'm actually going to do is put a little bit of cream in it. See if this works. OK. Yeah, OK. It looks better up there than it does down here. So if I now stir this, this is actually quite viscous. And what it means is the motions that I put in it are going to damp out quite quickly. And so as I actually move this around, you can see that actually we're not getting a lot of mixing here. These things actually aren't mixing up. So as I do this, I'm sort of getting more and more spirals. But it's not mixing together. It's not becoming homogeneous. Because as soon as I put in a motion, it's damped out very quickly. So this is not a turbulent medium. This is very viscous, and so the flow is essentially laminar. And it means that I can actually sustain these actually remarkably small-scale variations from one to another. So that's viscosity, which is stopping the turbulence happening. I don't want that on my soup. So soup is therefore quite viscous. So it's more viscous than most things, most fluids. So one that is less viscous is tea. So sad to say, this isn't Alice's tea. I was hoping it would be Alice's tea, but it's college catering tea instead. Tea. So tea is essentially water, and it's a lot less viscous. So in this case, if I put any kind of motion into this, I'm expecting that actually it's going to mix very quickly. It might actually mix immediately. I don't know. Let's see. OK, so the milk's all gone to the bottom. If I even do just very gentle motions here, then you can see that, oh, well, strong tea. Wow. Well, you'll have to trust me on that. That is actually brown now. Can you see? Yeah, there you go. So, all right. I was going to drink it. I'm not sure I'm going to drink it anymore. So in tea, it mixes almost immediately, and that's because it's not very viscous. So as soon as I move the motion of the fluid at all, it generates all these little eddies, all these little swirls, and they mix up the milk extremely quickly. So this is a case of a medium which is not very viscous, and so it can support the turbulent motion. That is strong. I think I'll leave that now. OK, so that's enough of the visualizer, I think. So when a medium has sufficiently large motions in it that the viscosity doesn't damp them out, we can get to turbulence. And in fact, space plasmas have incredibly low viscosity, so their Reynolds numbers are mind-bogglingly high. So in fact, they're almost always turbulent. OK, so turbulence generates mixing, as we sort of saw with the tea, and viscosity is there to damp out turbulence. OK, but we're not making that much progress. So what does this stuff actually look like? Well, Leonardo da Vinci wasn't an idiot, and this is a sketch that he drew just over 500 years ago. And this is actually a remarkably, impressively precise description of turbulence in a drawing. So what you can see here is a flow coming in into a large tank. And you can see the flow as it comes in is actually smooth. It's essentially laminar. But as it hits this tank of water, it does what we all kind of know it's going to do. It swirls around, and it produces large-scale swirls. And what Da Vinci actually drew here was large-scale swirls, smaller-scale swirls, you can see here, and little teeny tiny swirls down here as well. And that's very characteristic of turbulence. So as we put the energy into the system, it's being driven by the water coming in. That's producing the large-scale motion. You can see that large-scale motion breaks up. So you can think of this as swirls or eddies. And these eddies gradually break up, and they form smaller eddies and smaller eddies with actually smaller and smaller amplitudes until eventually they get sufficiently small that they're not large enough to survive the viscosity, and they get damped out. So this actually encapsulates almost everything we think about turbulence in one drawing over 500 years ago. It's quite remarkable. And this really is our view still of turbulence. It's this idea about, we can think of it in terms of eddies. We have large-scale eddies at a kind of driving scale, and that was me sloshing the water around in the washing up bowl. And these gradually break apart into smaller ones and smaller ones and smaller ones until eventually they get damped down. So that view of a hierarchy of eddies, a cascade of energy from large scales to small scales, was actually due to a guy called Fry Richardson. So Richardson was actually a really interesting chap. He did lots of interesting things. He was a pacifist, and he started studying the statistics of wars to try and understand how we could stop fighting each other. He did lots of other things too. He was one of the pioneers of what we now know as fractals, and he was one of the first people to talk about how measuring the length of something was different if you used a different length ruler. And actually, fractals is something that's really important in our study of turbulence as well. He also was very interested in weather and in the atmosphere. And in fact, he was the first person to ever attempt a numerical weather forecast for a country. So he actually, this is long before electronic computers, so it was all done by hand. And he took observations of the weather and tried to iterate them forward to make a prediction about what the weather would be later on. So he was a true pioneer of numerical weather forecasting that we all depend on day to day now. And in fact, he was a pioneer in many ways. He set the precedent because the forecast he produced was utterly hopelessly wrong. But he was also very interested in turbulence, and as I say, this idea of a cascade was due to him. And he even, these were the glory days of science, as well as coming up with the idea, he even came up with a poem to describe it. So this is the poem. It kind of sums it all up. Big worlds have little worlds that feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. So, you know, you can't say it better than that. That's what's going on. So we therefore have this picture of all these eddies. So we put energy in, all these eddies swirl around. But as they do so, they decay, and they gradually transfer energy to smaller scales. And what's interesting about that picture, if I actually go back very briefly to this one, all these eddies, I could never tell you whether there was going to be an eddy of a particular size in a particular place at a particular time. So they're unpredictable, they're random from that point of view, they're in fact chaotic. But on the other hand, I could tell you on average what the eddy properties were going to be like, on average for a particular size, how large amplitude they were going to be, what the velocity fluctuation was going to be across them. So turbulent media are predictable on a statistical point of view, but they're not predictable on a point-by-point point of view. So, so we can predict their average properties, but we really can't make any progress predicting their discrete properties at a given moment in time. That's incredibly hard. And so what that means is we have to take a statistical approach to analyzing them as well. So we end up using large data sets and number crunching them to try and make some progress. And actually, there's a sort of abiding mystery of turbulence in this picture as well. Where do the eddies come from? They're not in this smooth laminar flow that comes in. There are no eddies there. And yet, turbulence spontaneously generates these eddies. These structures, which are very characteristic, they get generated seemingly from nowhere. It's not obvious where they live in the hydrodynamics equations, the Navier-Stokes equations, and yet they come seemingly from nowhere. It's still no one really understands this, and it's one of the key properties of turbulence. Okay, that's a kind of hand-wavy definition. There is something a little bit more mathematical in turbulence as well. I'm not going to go through this stuff in great detail. There are actually very few exact, robust numerical results in turbulence because it's a really hard thing to study. It's been described as the last great problem of classical physics. But there is one really robust result, and this was due to Andrei Kolmogorov in 1941, who predicted how the power spectrum should scale. So this is a case for homogeneous isotropic stationary turbulence. So that just means I'm sloshing around my washing up bowl at a regular rate and just keep doing it. So I've got a constant rate of energy input. And this is a power spectrum, so this is basically the square of the amplitude of the fluctuations as a function of their scale, from large scales to small scales. So to put it in context with Da Vinci's diagram, the large scale is up here. That's the kind of swirling scale where we put the energy in. The medium scale is somewhere in the middle, and the little teeny tiny ones are at the bottom, where viscosity damps them out here. And what Kolmogorov said is if you've got that situation with this constant energy input and therefore constant energy output at the bottom, then this power spectrum on a log-log plot will scale with a slope of -5/3. And this is a very celebrated number. And in fact, this is an experimental measurement here, and you can see it actually fits incredibly accurate. So this is a very robust result. Okay, so that's turbulence on the Earth. What about turbulence in space? Well, we want to go out and measure turbulence in the solar wind. So first of all, we need to be confident there is that swirling scale there. And in fact, there is, and this is why. This is a movie taken across the sun's surface, and you can see the magnetic field lines all sloshing around here. And this is due to motion in the photosphere, and that drives waves that get carried out in the solar wind. And they are really the sloshing source, the energy source for the turbulent cascade that we measure. Fine, so there is turbulence there because it's being driven. But the question then is, how are we going to measure it? Well, that turns out to be relatively straightforward. You just need a friend with a few £100 million, and if you've got one of those, you could then go and build a spacecraft and fly it into the solar wind. There's one. And this one, to me at least, is a little bit special. This is Ulysses. So Ulysses is a child of the 1980s, in fact. It launched in October 1990. It was a European Space Agency mission, but with a large NASA involvement as well. And this is the dish that communicates with the Earth. And it carried on it a range of instruments to measure plasma properties, velocities, densities, temperatures, and also things like radio waves and cosmic rays and so on, but also magnetic fields. Now, Ulysses was launched in October 1990. I started my PhD here at Imperial College in October 1992. And this is special to me because I did my PhD on data from this spacecraft. But as you will realize from those dates, I never actually saw it. So you've seen it as well as I ever have. And in fact, this is a bit of a recurring theme of my career. So I've never actually seen a spacecraft that I've worked on. And I'm hoping someday to change that, but we'll see. So what's special about this, for me and for Imperial College, is that the magnetic field instrument, the instrument here that measures the magnetic fields in space, was actually built here at Imperial College. And Andre here was actually the leader of that instrument. So there were two sensors. There's a sensor here in black, which was actually built at the Jet Propulsion Laboratory. And there's another one right at the top. And this is the engineering model, one of the development models for that instrument. And I don't know if you can see, this is actually the little unit that was up at the top there. It does just look like polystyrene covered in aluminum foil, but I assure you it is actually an extremely high technology device. These are incredibly sensitive things. The magnetic fields in space are very, very small. They're just a few nanotesla. So to put that in context, that's about 10,000 times smaller than the magnetic field in this room, which we can't measure, which can't feel at all. The strongest magnetic fields that we generate day to day are in MRI machines in hospitals, and they're about 1 nanotesla. So the fields that this measures are a billion times smaller than that. And in actual fact, in principle, this sensor could detect the operation of an MRI machine at about 1 kilometer. So they're actually remarkably precise devices. And that's the electronics box that goes with it. Okay, so it's an important instrument for Imperial College, and certainly for me. And so Ulysses measured a vector magnetic field once a second for about 18 years. And at the end of that time, it was actually turned off. So Ulysses now drifts silently, sort of barely remembered in space. So no one will ever see the spacecraft again. It's out in the middle of nowhere. It's all very sad. And Ulysses actually went over the poles of the sun. It's the only spacecraft to have done so, and no one's going to do it again anytime soon. And that actually turned out, for various reasons, to be really good for studying turbulence. It never went closer to the sun than the Earth, so it was far away. But nevertheless, that turns out, for various reasons, to be a great place to study turbulence. So I ended up doing a lot of turbulence studies during my PhD. So if you do that, as I say, you have to do a kind of statistical thing. And after a while, you just end up spending a lot of time looking at wiggly lines on plots. So I actually find that quite interesting, but I do realize most people don't. But I still think you should look at some data. I think it's really important to look at data. So I'm going to show you some data now. So, but rather than just showing you wiggly lines on plots, let's show it as it goes past. So these are real magnetic field measurements from Ulysses. And what happens is the spacecraft sits there, and the solar wind flows over the top of the spacecraft, and it carries the magnetic field with it. This is speeded up about 100 times, because otherwise it really is boring. But what you can see here, I hope, is lots of little wiggles all the time. Those little wiggles are the turbulence we're interested in, all the little wiggles like that. But if you wait for a while, gradually over time, you realize the average direction has kind of changed a bit, and it gradually kind of changes from one to another. And that's these large-scale Alfvén waves that are kind of sloshing the turbulence. So in here, we've got the small-scale stuff, but we've also got the large-scale stuff at the same time. So the question is, well, how can we make progress? That's all very well. What are we actually going to do? Well, in fact, probably the easiest thing to do is just to take a power spectrum. So let's do that. And in fact, what we get here is a range of scales where it's turbulent, and here the spectral index is once again -5/3. So that's exactly what we see in neutral fluids. So that's fine. So we're done. That's easy. You know, that didn't take me long. And in fact, this has been known for a long time. But in fact, this isn't the whole story at all. And in fact, this is actually quite surprising. So the theories of plasma turbulence say it shouldn't look like this at all. So you remember from the slinky coil earlier, we were saying that actually there are Alfvén waves. So the turbulence in plasmas isn't really eddies. It's Alfvén waves moving around, or the eddies are made of Alfvén waves. And they move. And as a result of that, the two waves going past each other, they decorrelate. And so it makes the cascade slower. And as a result of this, the prediction was the spectral index here should actually be 3/2. It should be a flatter spectrum. That's really not what we see. This was an abiding mystery. And this is, in some sense, solved now, and we understand this better now through some theoretical developments that happened in the 80s and the 90s, where people realized that actually the eddies shouldn't actually be isotropic. They should actually gradually become long and thin along the magnetic field. And partly that's just because the magnetic field lines are hard to bend, so you can't kind of tangle them up as much as you would like. So the prediction then was these eddies would become long and thin. So the question is, how can we actually measure that? So that's what we set out to try and do. And actually that turns out to be quite hard. So as we've said, the solar wind goes past us, and there are these eddy structures. How do we know what they look like? We can't ever look at a single eddy. And in fact, so if you imagine a single structure going past, so all I get to do is look at a single strip of it. So there's a strip of a thing. So then you've got to work out what the thing is. So you can all make your own bet as to what the thing is. So, okay, so you've got an idea in your head what it's going to be like. So from a single strip, it's very hard. But if I get enough strips in enough directions, I can start trying to build up an idea about what this thing actually looks like. So if we just keep going for long enough, then it turns out not to be what perhaps you originally thought it was going to be. So this is what we're going to try and do in the solar wind. What we're trying to do is look at these things in lots of directions. So the analogy here is I've got a set of magnetic field lines that wiggle around. These eddies are actually all aligned along the magnetic field. With a spacecraft, I only go through it in one direction, so I just see a few of the eddies. But you can see here, because they're aligned with the magnetic field direction, as that field direction changes, in actual fact, I look through these eddies in different directions, so they pan around. So I can start trying to build up a picture. And in fact, if I go through an eddy almost perpendicular like this, so when the field is at a large angle, I'll see a very quick wiggle, so I'll see a high power. Whereas here, it takes a lot longer to go through it, so I'll see a lower power. So in other words, we realize what we should do is go and look at how the power level varies with angle in the magnetic field. So let's actually brace this up. Let's actually do it. There you go. So this is greatly speeded up. The white line here is the magnetic field direction. It sloshes around very quickly. That's due to the alpha in waves. And what we're doing is we're calculating the power on little scales all the time. And we're putting it in the right place, depending on what the angle of the magnetic field is at the time. And the radial direction here is straight up. Red's a high power, green's a medium-y power, blue's a low power. And you can see, actually, it's very rare for the magnetic field to point straight up. And that's just a solid angle effect. But when it does, we tend to see a lower power. You can see that actually already the arrow is actually increasing, because what I'm doing is making them longer where the power is lower, because that's lower power means a larger eddy size. And as this thing gradually builds up, and now we're getting enough that we can kind of see the picture gradually emerging, we're almost kind of tidying up now, you can see what comes out is something that actually is longer in this direction. And that tells you that these things are actually extended along the magnetic field. So again, we need to do this in a statistical way, and actually there's about 2 days of data in this. So, and normally we actually use about 30 days to do this. But we have to do this in a statistical way. Okay, so that's at one scale. And in fact, you have to do this at lots of different scales to see how these eddy shapes are at different scales. So if you go and do that, you end up with this. So this is what the eddies look like, sort of, in the solar wind. This is large scales, and this is small scales. So the large scale end, the relative sizes aren't right here, because the red ones are about 100 times bigger than the blue ones, but I couldn't get it on the plot. And you can see at the large scales, they're kind of isotropic. They're sort of sphere-like. And as we go to progressively smaller scales, they get longer and thinner along the magnetic field, exactly as we expect. I should say the ones that you think are small actually aren't that small, so that's the Earth in comparison. So these are still quite large things in the solar wind. So this is kind of what we thought would happen. This requires a lot more work than it looks like here. And in fact, you could do more quantitative things as well. So this is some really nice work done by Robert Wicks when he was here. And this shows you the spectrum that we saw before with this 5/3 spectrum. And if you just look at those times when the field is parallel to the flow, which are very, very rare, you have to work so hard to pull them out, and do clever things with wavelets. If you do that, you actually see this very different spectrum. This is a -2 spectrum. And they join at the top, and that's where the eddies are isotropic. And as the parallel spectrum drops off, they become more and more elongated along the field. In fact, there's a theory which predicts how elongated they should become by arguing that the timescales of the nonlinear decay and this propagation should be equal. That's known as the critical balance theory. Goldreich and Schudhauer in 1995 first proposed it, and it's become popular in many fields of turbulence study. And in fact, this is exactly the prediction we expect from critical balance. So in some sense, we're relatively reassured that this does seem to work. Okay, so that's fine. People who are interested in turbulence find this interesting, but maybe nobody else does. Why should we care about these things? Well, actually, the turbulence itself matters for various reasons. So let me just tell you about a couple of them. These very long, thin eddies actually tangle up the magnetic field lines. So just to give you an idea, this is a box with some magnetic field lines in it. And these are the magnetic field lines if I've just got some waves propagating along the magnetic field. So you see they all stick together as they wiggle up and down. These are just infinite plane waves. If, on the other hand, I put in turbulence with the kind of anisotropy that we saw here, you see these field lines deviate in lots of directions. So if I put a little particle running along one of these field lines, it's actually going to, on average, deviate away from the average magnetic field direction. So this is known as field perpendicular diffusion. So that actually turns out to be important in the propagation of energetic particles in the heliosphere. So let me show you a quick movie. This is an artificial eclipse generated by a spacecraft called SOHO. So the sun's visible disk is the size of the circle in the middle, and there's a darker circle around it, and that's the occulting disk, and this is the pin that holds up the occulting disk. So basically the spacecraft is sticking its thumb over the sun so that it can see what's going on around it. And you can see here a big eruption of material off the right-hand side. And associated with that, straight afterwards, you can see what I'm old enough to think of as static on the screen. But it actually isn't. Each of these streaks is a single particle traveling relativistically that hits the detector, and it comes up as a little streak. This is a CCD detector. Each one of those particles was accelerated near the sun, and they're traveling relativistic particles. They can knock out spacecraft. And they propagate along magnetic fields. And so this tangled magnetic field structure actually turns out to be very important in controlling their propagation. So we're really just at the beginning of trying to apply our understanding of anisotropy to the propagation of those particles. But it's a potentially very important subject. The other thing I should mention very briefly is Tokamaks. So MAST, the mega-amp spherical tokamak, is one of the few places on Earth where you can actually find plasmas for any length of time. So this is one of a number of machines around the world where people are trying to confine plasmas at very high temperatures, and they do that with magnetic fields. There's a very strong magnetic field, and hopefully you can see the swirly pattern of the magnetic field lines here. This thing is a few meters across. It's in deepest Oxfordshire, and the head honcho of Column is here as well, so thanks for coming, Steve. And these machines, the goal eventually of these kind of machines is to confine a very hot plasma for long enough that the nuclei actually fuse and generate power. So the ultimate goal is to produce clean, cheap power through fusion. It's really hard to do that. And it's really hard because the plasma wants to get out. It's always struggling to get out. So the big problem is confinement. How do you keep the plasma in? And there's various ways that the plasma gets out, but one of those is turbulence. And again, we saw earlier the mixing is very important in turbulence. So the turbulence actually near the edge of the plasma here actually helps some of the plasma get out, which is exactly what you don't want. So it's of interest to understand the plasma turbulence within these machines to try and understand confinement better. So recently, I spent some time in Oxford using some data from a new, really interesting diagnostic inside these machines to try and understand just the structure of the turbulence better. It's actually really hard to do because you can't stick things in these because they melt. These things are really, really hot. So we actually used the kind of techniques we developed in space to try and work out what the structure of these eddies are inside mass. It's very much a work in progress, but it turns out they're quite long and thin. So they're a couple of centimeters across, and they're on the way towards a meter long. So actually, when you see that picture and then you look at that, you probably shouldn't be too surprised. But nevertheless, there are some really interesting questions as to why they are the size that they are, and it's very much a work in progress. But that's one of the things that we're doing at the moment. And I would be remiss if I didn't mention future spacecraft as well. So I've talked about Ulysses, where the magnetic field instrument was actually designed and built here at Imperial College by a bunch of very clever engineers upstairs. They're building magnetic field measurement instruments for other missions as well. And one of those in the future is Solar Orbiter. So Solar Orbiter is a mission led again by the European Space Agency, again with actually large ESA involvement, with NASA involvement as well. And it's actually got a large UK contribution of instruments on it as well, and they're funded by the UK Space Agency. And the spacecraft itself is actually being built by Astrum in the UK, just behind a multiplex cinema in Stevenage, in fact. And so you think that's a joke, but it's not. So Solar Orbiter is going to be a really interesting spacecraft. It's going to fly very close to the sun, closer in than Mercury, take pictures of the sun, and also measure the solar wind and the magnetic field coming out. And it's not really designed as a turbulence mission, but in fact it's going to be very good for turbulence as well. So we're really looking forward to that. And the magnetic field instrument is being built at Imperial College as well, so that's very exciting for us. And along with Solar Orbiter, NASA is actually building a spacecraft in the same timescale called Solar Probe, which is going to plunge even closer to the sun. And I think the combination of the two are really going to help us understand plasma turbulence more than we've ever done before. So we're very excited about that. That's launching in 2017, so pace yourself, but it's going to be great when it goes. Okay, so in the last couple of minutes, I'd just like to say a few thank yous, if you'd indulge me. First of all, I should say thank you to everyone for coming. So I'm aware that there are people in the audience who've really traveled quite large distances to be here, so I'm genuinely very grateful. So thank you very much indeed for coming. I should thank some other people as well. So PhD students and postdocs that I've worked with, they've all actually done really good work, and I've been really fortunate to work with a really clever bunch of people. But when I was thinking about this, I realized that actually I was much more fortunate than that, because I actually worked with a really nice bunch of people, and I actually really enjoyed working with all of them. And that didn't really have to be true, but it is. And so that's a genuine relief looking back on it. And I think they've done really good work, so I'm grateful to all of them. I've also collaborated with a few people over the years. I think over the years I've come to realize actually I'm quite bad at collaborating with people. But nevertheless, I have collaborated with a few. So one mission that I haven't talked about at all is Cluster, which was another one led by Andre at Imperial College, actually, with the magnetometer. And Elizabeth Lusek and I were both postdocs here from about 2000. And in fact, we were both very lucky, because Andre essentially gave us this brand new, unique data set and kind of let us do whatever we liked with it. So we spent a really productive and very happy few years just working on this fantastic data set. So I was very, very lucky. So thank you for that. And I think Elizabeth and I did some interesting work. A lot of the stuff that I told you about today, I did in collaboration with Miriam Foreman, who works in Stony Brook. Neither of us worked very quickly, so in fact, it took about a decade to get this work out, so that doesn't bode very well for REF. But nevertheless, it's been a real pleasure to work with Miriam, although it was difficult on such a large distance. There was a lot of Skype. And then more recently, I've been working with Alex in Oxford, who's a real proper Russian theorist, and I think we complement each other quite well. And for example, the Tokamaks stuff I've been doing with Alex more recently. These four people have been my bosses. So Andre was my supervisor, and then my boss afterwards. David at Queen Mary, and then Peter and Steve here at Imperial College. And again, I've been very lucky, because actually all of them have really been supportive over the years. It's one of these things you come to realize just how important it is to have bosses who are advocates of what you do, who actually push hard for you. And in all of those, that's been the case, and I'm genuinely very grateful. But Andre in particular, I guess PhD supervisor is particularly influential. But as anyone who's worked for Andre will tell you, actually, when you work for Andre, he kind of takes you under his wing, and you become part of the sort of extended Andre family. He's very protective of the people that work for him, and really pushes hard for them, and it really makes a big difference. And I can see many things in my career that have happened because Andre worked sort of semi-scheming in the background to make them happen. So some of those, in retrospect, I worked out. Some of them, I suspect I never will work out. But some of them were quite blatant. So I remember once sitting in my office. I've never seen Andre run, but I did once hear him run. And I was sitting in my office, and there was compliment. And Andre suddenly put his head around the door, slightly flustered, and he just said, "The phone's about to ring. Pick it up. Say yes." And of course, he was right. So thank you, Andre. Over to you. And then finally, I should say thank you to my mother. So Jennifer is, has been supportive in the way that only mothers can be over the years. And she's one of these people that life kind of throws things at her, and she just keeps going. So even by her standards, she's had quite an exciting year. And so you'll see her later on, she might well be in a wheelchair, because about 8 weeks ago, she had a bit of an exciting incident in the Albert Hall, and her right leg now looks like this. So if you're not squeamish, or you want to find out if you're not squeamish or not, I challenge you to go and talk to her and ask her how she got out of the Albert Hall. But in any case, just be careful of her right leg. She had the cast off last week, so just don't touch. Okay, and finally, I should say thank you to Antonetta, my wife. So Antonetta has been hugely supportive over the years, and I'm very grateful. So I'm very happy to say thank you, not just because she told me to, but she has been hugely supportive over the years, and kind of running all the practical stuff that otherwise I would be a bit hopeless at, as anyone who knows us knows full well. And I will sort out that kitchen at some point. Okay, so finally, I should finish just very briefly. I was listening to the radio last week, and I was listening to a panel show, and in fact, on the panel show was my wife's favorite comedian, so the thinking woman Stephen Fry, David Mitchell. And he was actually, purely by coincidence, he was talking about space, and he was talking about the exploration of space, and he was talking about space scientists, of which there are actually a fair number in this room today. And what he said was, "I think it's very sad that such large sections of our society are living in a dream world, and that they're given the funding to continue to explore this fantasy. But it's totally pointless, and we need to grow up and keep out of space. There's nothing there, the clue is in the name." Well, I hope I've been able to persuade you that actually there is something there. I don't think the study of it is completely pointless. I've been living in that dream world for about 20 years now. I'm quite enjoying it, and I hope to be able to do so for quite a while to come. Thanks very much for coming. Thank you.